We're going to have a look at continuity and smoothness of a piecewise functions. Now we've done this a little bit before, but as you can see in this particular function, you can see that the second function, y2, is in fact a quadratic. And so the joy of piecewise functions is that you don't have to connect lines to lines. You can connect lines to quadratics and quadratics to cubics and cubics to exponentials and everything else. So give us a lot more power in terms of being able to string together very different functions all together. So let's have a go at sketching this so we can determine whether it is continuous and or smooth. Now, if we were only trying to do continuity, well, we only actually need to check one point, x equals 4. That's the changeover from this function to this function. So x equals 4 is the problem point. So let's just do the continuity bit first. So if we were just interested in continuity, this would be the thing to check. So we'd sub x equals 4 into y1, and then we would do the same into y2, and then we'd just check that they match. We're going to need to do a little bit more later, but I think this is a good starting off point anyway. So we get y1 is equal to a half times 2 minus 2. A half times 2 is 2. 2 minus 2 is 0. And for y2, it would be equal to negative 4 minus 4 squared, which is negative 0 squared, which is just 0. So you can see that they do in fact match. Therefore, it is continuous. Alrighty, so we don't need to do any more work if we were just trying to do continuity. However, we also want to look at the smoothness, and I think for smoothness, we're going to have to look at a graph of it. So we'll put what we've done to the side, and we will continue on as though we were just trying to do it properly. So let's draw up a table of values so we can sketch this function nice and easy. So we got x and y. And we've just got to remember that depending on the values is going to depend on what we get. So let's do a few negatives. So we'll have negative 1, 0, 1, 2, 3, 4 is the problem point, and we might just do 5 and 6 to get a few on the far side of the problem point. Now, thankfully, for the majority of these, the definition is entirely based on y1. And so y1 is a linear function, which means once we learn what the pattern is, it's going to be nice and easy to work out the numbers. So let's try it. So for x equals, oh, actually, let's use function notation. Let's change this to f of x, okay? So f of negative 1, well, negative 1 is less than 4, so we're substituting it into y1. A half times negative 1 minus 2 minus a half minus 2 is minus 2.5, or minus 2.5. For f of 0, we're still substituting into the same function, so it's going to be a half times 0 minus 2, it's negative 2, and at this point you realize that it's a linear equation, and since we're doing one step to the right, it's just going to follow the movement of the gradient, which in this case is plus a half. It's going to be negative 1.5, negative 1, negative a half, negative 0.1, or 0.5 if you're playing at home. And it's at 4 where we have to remind ourselves that it's only a linear function up to x equals 4. After that, it behaves like a quadratic. Now we already know that it matches, but this is where you would probably substitute into both y1 and y2. We've already done that and seen that we get the same output, so we don't have to stress. And instead, we can just work out f of 5 and f of 6. Otherwise, we would have to, like we did before, substitute it in twice. So f of 5 is going to be equal to negative 5 minus 4. 5 minus 4 squared is 1, negative 1. For 6, we've got negative 6 minus 4. 6 minus 4 is 2. 2 squared is 4, so it's a negative 4. So we get negative 1 here and negative 4 here, and we are ready to actually sketch our graph now. So let us have a look at what it's going to look like. I'm going to move all my working out of the way. Alrighty, so you can see I've set up my axes. And now I'm just going to plot all my points in, and I'm just going to do it in 2 different colors because I've got my linear equation to there, my y1, and then I've got my y2 in this color, just to make it nice and clear. So at -1, it's at -2.5, then we're at 0, -2, then we're at 1, and then we're here, and it's when we hit 4, 0, which is when our blue is going to finish, and it connects perfectly because we worked out before that it is continuous, so they connect 100%, and the next point is going to be at 5, -1, and then at 6, -4. Alrighty, so now we can join them up. Now we know that a straight line means that it's going to look like this, and I might even extend it out a little bit. So you can see that is the y1, the blue part of the function, and then for the second part of the function, it's going to come out like this. Look like a quadratic on the far side. And so the question now becomes, we knew it was continuous, we worked that out right at the beginning. The question is it smooth? And some of you might look at this and you might say, well, it looks kind of smooth. I see a tiny little point. It's not very sharp, but I would say it is not perfectly might not be bumpy, but it is certainly not perfectly smooth. Now, we are going to rigorously define smoothness later in the same way that we've already rigorously defined continuity. So we're going to make it so that it's crystal clear and we're not just guessing and looking at a picture, but we can have a look at a Desmos version of this and just double check that it looks the same. You can see on the left that I've put it in properly, and if we actually have a look, you can see that it's not hugely, but there is a slight little bump here. You can see it just a little bit, that there is a slight little bump. So it's not that it's crazily, but it is not smooth. It is not perfectly smooth. And so if it's not perfectly smooth, then we cannot say that it is perfectly smooth. Alrighty, so there you go. That is how you can tell the continuity and smoothness of a piecewise function by sketching it. I'll see you in the next one. Goodbye.